Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor in the Department of Economics at Aligarh Muslim University. This lecture would be on the concept of dummy variable and its applications and uses over there more particularly in econometrics and in economics. Before starting with the discussion on dummy variable, let us take another case of another story of a chow test. It sometimes happens that your sample of observation consists of two or more subsamples and you are uncertain about whether you should run one combined regression or a separate regression. Like suppose you want to study the relationship of between foreign exchange and economic growth. Now, before 1991, our trade policies were of a different nature and more particularly of import substituting. So, we didn't have a very strong foreign exchange reserves. But after the policy of 1991, things changed. Now we are having, at the current moment, we are having a huge foreign deposits. So, shall we take the period, say from 1960 to 1990, a different one, we conduct a different regression, and again from 1991 till date, shall we conduct a different regression, or we can, the other thing can be, we can simply join all of them together. So this is a case wherein we have to be very clear what is to be done. Say we have a sample consisting of two subsamples and that you are wondering whether to combine them in a pooled regression or run a separate. So we will denote the residual sum of squares or of the subsample regression as RSSA and RSSB. So when we denote RSSPA and RSSPB, the sum of squares of the residual in the pooled regression for the observation belonging to the two subsamples. Since the subsample regression minimize RSS, that is your residual sum of squares for their observations, they must fit them as best as well and generally better than the pooled regression. Thus we can say that this regression, this is residual sum of squares for A is less than or equal to the residual sum of squares for the pooled one, and the residual sum of squares should be less than or equal to the for B should be less than or equal to residual sum of squares of pooled one. Or we can say that that RSS, the residual sum of squares for the equation A plus B, the residual sum of squares for equation B, it should be less than or equal to the residual sum of squares for the pooled regression. Now, see, equality between this, if there is an equality between this, the pooled one, that the residual sum of squares for the pooled regression and the residual sum of squares for A and B, equality will occur only when the regression coefficient of the pooled and the subsample coefficient coincides. But in general, there will be an improvement, that is in general there will be an improvement when the sample is split up. But there is a price to it. You are splitting the sample very well. Then the price is you have to pay in terms of the degrees of freedom, because more degrees of freedom, the k degrees of freedom are used up, since instead of k parameter for the pooled regression, we now have to estimate k for each subsample, making 2k in all. So after breaking up the sample, we are still left with residual sum of squares A plus residual sum of squares B, that is the unexplained sum of squares of the residuals, and we have n minus 2k if remaining. So there will be an issue with this degrees of freedom. So what we do, in chow test we used up this formula That is basically the structure of the formula is improvement in fit divided by the extra degrees of freedom used up divided by whole divided by the residual sum of squares remaining divided by the degrees of freedom, or more specifically we can define it in this term, that is RSS pooled minus RSS A minus RSS B divided by K, the whole divided by residual sum of squares for A plus residual sum of squares plus B divided by n minus 2k, which is distributed with k and n minus 2k degrees of freedom under the null hypothesis of no significant improvement in fit. This was the basic way of checking through Chow test, whether you should use 2 regressions or you should use one regression when we know there is a significant change at one period of time. Now let us see the same thing with a different perspective. We see the same thing with a different perspective, like we say, we construct a different type of regression. It reads yt is equal to alpha 1 plus alpha 2 dt. dt means here this t will be, we will say t is 1 if the period is from say 1960, we are doing a study from 1960 to 2022. We are studying the relationship between consumption and income. We are studying the period for 1960 to the current period to 2022 or 2023, and now we know that there has been a change, a significant change in 1991. So what we do, we divide the time period, we take 2 separate time periods, one is from 1960 to 1990 and the next time period is from 1991 to here 2022. Now if what we simply use a technique, that is we are using a technique of dummy variable wherein d will be equal to 1 for the period 1960 to 1990 and d will be equal to 0 for the period after this 1990, that is from 1991 to 2022. See, our Chow test used to tells us only if 2 or more regressions are different, without telling us what is the source of difference. The source of difference can be found by pooling all the observations and running as one single multiple regression. That is what we are showing over here. We will be elaborating the process further. So we take the same equation. When the period is 0, so when your period is 0, this becomes 0, this becomes 0. So this entire thing, it becomes 0, this entire thing becomes 0. You are left with only alpha 1 plus beta 1 xt. Or ut is there, at the moment we ignore it. Then for the consumption function, it is mean, when the mean consumption function for the period from 1991 to 22, now this is equal to 1. And we have, now when this is equal to 1, it means this is also there. This earlier it would become, the entire term becomes 0. Now this is 1, so this term is there as it is. So we get alpha 1 plus alpha 2. Now this is also not 0 anymore, this x is also 1. So you have a value over here, so we now combine this and we can write it as beta 1 plus beta 2 xt. Here alpha 2, earlier in this equation for the period before 1990, there was no alpha 2. So alpha 2 is the differential intercept. In this equation there was no beta 2. So beta 2 is the differential slope coefficient. So now we have the differential intercept indicates by how much the intercept of the second period is different from the intercept of the first period. And then the slope differential, that is beta 2, it indicates by how much the slope of the second period is different from the slope of the first period. That is, we can see by certain diagrams. So in this case, what we are saying, the intercept is the same for both. The intercept is the same, excuse me, but the slope here is different and the slope here is different. So if the differential intercept alpha 2 is statistically insignificant, we can say that both the regression lines have the same intercept, or we can say that like this. What we are checking a consumption income relationship. We can say, so if you remember your consumption income relationship, consumption is you can say that is autonomous consumption plus marginal propensity to consume multiplied with income. Now, so we can say that in both the periods, autonomous consumption component was the same. What was different was the the marginal propensity to consume. We can have another case. That is, if the differential slope coefficient beta 2 is statistically insignificant, but alpha 2 is significant. So we say that there is a difference in the intercept, but the slope is the same. So two lines are running parallel to each other. So what does this mean? This will indicate that the autonomous consumption has increased. Autonomous consumption has increased, but the marginal propensity to consume was the same. Whereas in the previous case, the autonomous consumption was the same, the marginal propensity to consume was different. If this is the case, this figure, it represents that the intercept is the same before and after 1991, and the slope is also the same before and after 1991. So both the intercept and and the slope is the same. We can have one more case. There is a difference in the intercept, there is a difference in the slope. So herein the intercept has also changed, that the autonomous consumption has also changed, and the marginal propensity to consume has also changed. So both the intercept and the slope are different over here. Now this is the beauty of dummy variable. Dummy variable, the advantage is it tells us whether the intercept is different or the slope is different or both of them are different. And an additional benefit is, since we are pooling, we are taking the entire data, say from, it was not that we are taking one from 1960 to 1990 and the another one from 1991 to 2022. We are taking all the data, we are pooling it together. So the pooling of the observations increases the degrees of freedom, and this will lead to the improvement in the precision of the estimated parameters. So now we take on the dummy variables. Why these dummy variables and what are the uses? See, dummy variable occurs, happens because of, I'll say, the temporal effect, spatial effect, qualitative effect and broad grouping. See, temporal effect, you can say that the change due to time. Say we want to see the impact of weather on wheat production. Now there were years of drought and there is a famine or war. To compute such type of incident, we employ dummy variables. Spatial effect is effect over space. Say we have a commodity and the relationship between price and production, it differs from market to market. So when we move from one market to the other, the change in price, it can be studied. Qualitative analysis, we can say that, we have consumption function and our hypothesis is the consumption patterns of male is different from the consumption pattern of females. So when, or the consumption is different across religion or caste. So again, these things can be studied over there. Broad groupings could be like we have quantitative data, and this is also we need dummy variables, like we want to study the impact of age on consumption income relationship of different age group. Say the age group of from 15 to 45, it consumes differently, and the age group after 45 and above, it consumes differently. So dummy variables can be used in all these cases. Okay, let's take an example. Say we have the consumption income, we want to study the consumption income relationship in two different periods. One is say wartime, and the another is when there is peace. So let us take the data. We are taking some hypothetical data over here, and say this 1990 is a period of war, 1991 is a period of war, then 1992 is a period of peace, then again 93 is a period of war. So a period of war is given a dummy 0, a period of war is given a dummy 0, a period of war is given a dummy 0, and a peace, the period of peace is given a dummy 1, peace, all these are given a dummy 1. So this what we can do, when we have this, all these three cases we can have, that the intercept is different, the slope coefficient is different, both the intercept and the slope is different. So now d is equal to 0 for wartime and d is equal to 1 for peacetime. Let us take each one of these three cases. Now when the intercept is different, we are talking about a case when the intercept is different, that is, when the intercept is different, we are applying what you have when d is equal to 0. 0 was the period of, if you go to 0 was the period of war. So when d is equal to 0, this term becomes 0, so you are left with alpha naught plus beta y. Now when d is equal to 1, that is in the time where it is a peace, then this 1 is there, so it becomes alpha 1 plus alpha 2, because alpha you can give it alpha 1 plus, this is, you can say alpha 0 alpha 1, so you can say alpha 0 plus alpha 1, you have alpha 1 plus is equal to plus by. So alpha here is equal, you have this alpha 2 is nothing but your, sorry, alpha 1 is nothing but your differential intercept. So this is the case when your intercept is different. Now the second case where the intercepts are same for both the periods, but the slope is different. Now here we have when d is equal to 0, so what you are left is, you are left with c plus beta naught y. And when d is equal to 1, then this term will also come into play. So you have alpha plus beta naught y plus beta 1 y. Now, so you combine these two betas multiplied by y. So this is the case where the intercept are different. Now if both the slope and intercept are different, this will be the different type of equation. You have alpha 0 plus alpha 1 d. Now you have beta 0 y plus beta 1 dy. So when d is equal to 0 in the time of war, so all this becomes 0, this becomes 0 in war, and in peace this is also 1, this is also 1. So for war it becomes alpha naught plus beta 1 y. In the time of peace it is alpha naught plus alpha 1 plus beta naught plus beta 1 y. So this is how you apply intercept, the dummy variable. Another example for your illustration, we have, say we are studying the nature of these teachers in the school. They are trained and untrained teacher. So we have this equation, S is equal to, that is the salary is equal to alpha plus beta d plus EU. D stands for, we take D as a dummy for whether the teacher is trained or not. So D will be 1 if the teacher is trained, and D will be 0 if the teacher is not trained. So when your teacher is not trained, your D becomes 0. So what is left? You are left with only alpha. And when D is equal to 1, that is your teacher is trained. So you have here also alpha plus, so we take alpha plus beta. And if this beta is, say, statistically significant, it indicates that there is a significant difference between the salaries of trained and untrained teachers. Now we move on to the application of dummy variables. They are applied for finding the stability of the function, the seasonal effect, the piecewise regression and interaction effect. So this is the same example which we are having, which we had earlier, a type of example we discussed earlier. We are having two regressions. Saving is a function of income, and say we have the data of saving on income for the period from, say, 1980 to 2000, and then we know that some change happened in 1990. The saving function is equal to alpha plus beta y is the income plus u. We know, and we want to test whether there was a significant difference before 1990 and after 1990. So one way was to perform two different regression equations, first from 1980 to 1990 and the second one from after 1990, and then we compared these two. This was the process which we used to do through Chow test. But if we can use these dummy variables, we simply have to write our equation in this format. This equation is written in this format, where we had alpha naught plus alpha 1 d, and d is your dummy, alpha 1 is your differential intercept, plus beta naught y plus beta 1 dy, where d is again your dummy, and plus u, where d will take 1 if the saving data belongs to period before 1990, and d will be 0 if it is otherwise, that means it is the period after 1990. So this is how you check for the stability of the function, and whether your alpha is significant or your beta is significant. You take a decision, or whether your alpha has changed or your beta has changed, or if both your alpha and your beta has changed. So this expected saving for the period, you can, when d becomes 0, this is your equation, and when d is equal to 1, this is your equation. Your alpha 1 is the differential intercept and beta 1 is the differential slope. If alpha 1 and beta 1 are insignificant statistically, we say that there is no change in the relationship if both alpha 1 and beta 1 are not significant. If beta 1 is not significant and only alpha 1 is significant, it says that there is a change in the intercept. And the one case, if both alpha 1 and beta 1 are significant, it means that the whole relationship has changed from the period before 1990 to after 1990. So this is how we use dummy variables for the case of stability of a function. Now a very prominent effect is, we study a very prominent use of dummy variable is to study the impact of seasons. Like, see, profit is a function of sales, obviously. Also, season has an impact. Like, what is the season and in which season what things will be sold. So obviously, when on the basis of quantity sold, you have a different level of profit. Now, particularly in India, we have this 4 seasons. So what we know, we can incorporate the impact of seasons on profit by making this equation. By making this equation where you have alpha 1 plus alpha 2 d2 plus alpha 3 d3 plus alpha 4 d4 plus beta x plus u. At the moment, understand one thing, we will discuss that later, that when there are 4 seasons, in order to avoid falling into the dummy variable trap, we will make dummies for only 3 seasons, 1 less. If there are 4 seasons, we are making dummy for 3. If there are 2 criterias, if there are 2 categories, like we have seen before also in this wartime and saving function, one period is 1990, before 1990, and the other one is one after 90. We take only one dummy variable, d is equal to 1 and d is equal to 0. But here, and similarly in wartime, peacetime also, we were taking only one dummy variable when we have 2 categories. And so similarly, when there are 4 categories, there are 4 seasons, we need to incorporate only 3 variables. We will see its impact, why it is done just once we progress with this lecture. So again, so if how the dummies are formulated is very clearly given over here. If D2 is equal to 1, the data belongs to the second season or else otherwise. Similarly, if D3 is equal to 1, data belongs to the third season or otherwise if D3 is equal to 0. If D4 is equal to 1, the data belongs to the fourth season or D4 is equal to 0 otherwise. And we are saying that if there are 4 seasons, we take 3 dummy variables. Now, so for finding average profit during the first, because the first season dummy is not there, it means for the first season dummy it is nothing but D2 is equal to D3 is equal to D4 is all of them is equal to 0. So now we take, so for finding the first, for finding that is for the first season, we write the equation like this, and what we are left with is alpha 1 plus beta x. We are talking about this equation. Alpha 1 plus alpha 2 D2 plus alpha 3 D3. So what happens? This becomes 0, this becomes 0, this becomes 0, this becomes 0. So what is left? Sorry, not this bx is not 0. So all these 3 are 0. So what is left is alpha 1 plus beta x. Alpha 1 plus beta x. Next time, for finding the average profit during the second season, you have for the second season this is equal to 1, this is 0, this is 0. So these two cancelled out. So you are left with these two and this the last variables. So what you have? Alpha 1 plus alpha 2 beta x. Now alpha 1 here is the differential coefficient. So it shows how the average profit differs between the first season and the second season. If this alpha 2 is not significant, it means there is no significant difference between the profits of the first season and the second season. Now similarly we form for the third season. Now what happens in the third season? Alpha 2 is equal to 0. Now what you are left is alpha 1 plus alpha 3 plus beta x. For the fourth season, alpha 2 and alpha 3 they become 0. So you are left with alpha 1 plus alpha 4 plus beta x. So this is how we derive the equations for all the 4 seasons. We are talking about this equation, and we from here we make for whatever the dummy variable we are incorporating for whichever season we are having, others we make 0, and so we get for the first season this is the equation, for the second season this is the equation, for the third season this is the equation, and for the fourth season this happens to be the equation. So this is a way to use to incorporate the element of seasonality in your analysis. You don't have to break your data into a small summer season, winter season, autumn season, rainy season, and then do small regressions. You just go on with the calculation of one. You just formulate it with your equation with the help of a incorporation of dummy variables, and this equation can give you the impact of the seasons on the profit along with the sales of that commodity. Next, we move to piecewise linear regression. This also you can, we have discussed a case earlier also similar to this, that till 1990 the amount of foreign exchange reserves was it was increasing, but it was at a very slow rate. After 1991 your foreign exchange reserves has increased like this. So there is a switch, there is a change over here. So so this can be explained, or this can be used with this can be elaborated with the help of piecewise linear regression, or as an example is being shown, like in the case of a marketing where you are saying, okay, if you sell about 100 units, you will get 5% as commission. But the moment you have increased your sales beyond 100 units, then we will be giving you 7% commission. So the rate changes. Here it was 5% and here it is 7%. So there is a change in rate. So what we are studying a relationship that sales commission is a function of sales. Commission is equal to, now we write alpha plus beta 1 sales plus beta 2 S minus S asterisk. This point is your S asterisk. It is equal to, say, we take it as 100 as an example. If you are able to sell 100 units of the product, then after this your commission will change, that is it will become from 5, it will increase to 7%. So this S asterisk is nothing but this change over here. So this can be used by to incorporate. We have, so if the break-even amount is D is equal to 1, your S is greater than S asterisk, then it is, if you, the period where you have sold more than 100 units as such in our example, so total sales are greater than the sale when commission changes, or else it will be equal to D will be take 0. So in this equation, like in the previous equation which we are having, that is, the equation was C is equal to alpha plus beta S, beta 1 S or beta S. So where it was, this was the case where it was simply, it was not taking into consideration this commission thing, that if you are able to sell after a certain amount, your it is changing, your beta 1 is changing. So this equation is a sample regression without bothering about the twist or turn. It is, or you can say this will be the case when there is no commission. But in this equation, when you have incorporated beta 2, it gives the impact of sales on the commission. Beta 2, this shows how it will vary. So whereas beta 1 will give the overall time slope of the time before S asterisk, but beta 2, it will give you the case that after what happens when you have reached a particular S asterisk, a particular level of sales, after which there is a change in the commission. So that the slope after that, if there is, means you are able to achieve that S asterisk or the amount, in our case the 100 unit sale, so that after that your commission changes. So then after S asterisk your slope will be beta 1 plus beta 2. So again, you don't have to compute two different regressions for two different periods, one in which you have sold less than 100 and one in the other one where you are selling more than 100. And again, there's no fear of losing your degrees of freedom also. In one equation, you can incorporate the entire thing. The next is an interaction effect. This is again a very interesting application of dummy variable. Now see, you have gender and race. Both are qualitative variables. And you have another variable, education. It is quantitative. Now we assume that there is a differential effect of gender on education. So it is, now we take, means what we are doing, we are taking, we are taking the impact on wages. So we are seeing the impact of wage based on education. Obviously, if your education is high, your income will be, your wages will be high. But herein there is another thing which can play a role, that is, what is your gender. Also another thing that can be incorporated is, although we can take it in the US context, that whether you are a black or a white. So gender and race are qualitative, whereas education is quantitative. Now it is assumed that differential effect of gender dummy D1 is constant across the two categories of race, and differential effect of race dummy 2 is also constant across the two genders. That is, if mean salary is higher for males than for females, this is so whether they are black or not. Similarly, if the blacks have a lower mean wage, this is so because they are females or males. So what we do, we have dummy D1 is equal to 1 if it is female or otherwise, and D2 is equal to 1 if you are black or otherwise. So we are incorporating the impact of gender and race along with education, and we are seeing the impact of these three on the wages or the salary. And what we are assuming that the differential effect of gender dummy D1 is constant across the two categories of race, and the differential effect of race dummy 2 is also constant across the two genders. But in many cases this assumption may not be fulfilled. In other words, there may be an interaction term between these qualitative variables, that is gender and race. So that is, their effect may not be simply additive, but it can be multiplicative also. So in this equation what we have over here, this shows that the mean wages of female black are different by A3 from the mean wages of female or black. If all the three differential dummy coefficients are negative, this indicates that the female black workers earn much lower salary than female, they indicate that the female black workers earn much lower wages than female or black workers as compared to male and white race workers. So we can write this, after incorporating this, can write that A1 is your differential effect of being a female, A2 is the differential effect of being black, and A3 is the differential effect of being a female and a black. So both the things are incorporated over here. So what we can do based on whatever of them is significant, based on whatever of them are significant, we can come to a decision that if she is a male, or if the person is a male or female, is there any impact on the salary? If the person is a male and a black, or the person is a female and a black, what is the impact on the wages or the salaries? So that is, we are incorporating qualitative variables of like race and gender, and we are seeing its interaction with education and its impact on the level of income. These were the applications of dummy variables in different cases. Now we move on to the last topic for today, that is the dummy variable trap. The dummy variable trap is a phenomenon that can occur in statistical modeling, particularly in regression analysis, when categorical variables are encoded using dummy variables. Let us go quickly to an example of it. Now we are again studying the consumption income relationship. You have C is equal to alpha plus beta y plus u. Now suppose the slope remains same and only the intercept changes, then var and peace are the qualities which we want the dummy to represent. Now say we are taking a case, what we have seen, if it was a var time and peace time, there are two different categories, we should use one dummy. But what we are doing over here, we are creating a one dummy for war time and one dummy for peace time. We are doing a wrong thing. We will see how it is wrong. But herein, we are creating two different dummies for two categories. So D1 is equal to 1 if the data belongs to war time, and D1 is equal to 0 otherwise. And in the next time, D2 is equal to 1 if the data belongs to peace time, and D2 is equal to 0 otherwise. So what we have done, we are studying the impact, whether it is war on peace, on consumption, and what we have done, we have taken a dummy for war, and also we have created another dummy by peace for the peace time. Earlier the correct way basically was, when d1 is equal, if d is equal to 1 for var, d is equal to 0 for p's, but we are not doing this. Now this will lead to computational issues. Let's see that. We have the data for alpha 0, we have the data for alpha 1, we have the data for alpha 2, and we have the data for bt. So we write it in the form of a matrix. At the moment, just ignore the column for b. Now we can see that alpha 0 is the intercept. Now here there is the problem of, so we model our relationship in the form of a matrix. So we have this alpha naught, the intercept term, plus alpha 1 plus alpha 2, and we have a column for beta. At the moment we just ignore the column for beta. Now we see that when we are taking such a case that for two categories we have created two dummy variables, now there will a problem of multicollinearity will emerge. We can see that, see, column 1 minus column 2 is equal and minus column 3 is equal to 0. 1 minus 1 0, 1 minus 1 0. So this, now we are having a perfectly linear relationship. Now in the, or you can also say column 1 minus column 2 is equal to column 3. So column 1 minus column 2, 1 minus column 2 is equal to column 3. So there is a perfect relationship between column 1, column 2 and column 3. This is what it refer, this will lead to the problem of multicollinearity. Now the problem here is because of the first, I can say because of the intercept term alpha naught, which is there in the first column. If the intercept is removed, then the problem of multicollinearity is also solved. So for two dummy variables or for two categories, we should not have two dummy variables, or for two dummy variables there should not be this intercept term. So the solution to this problem is that we should always use one less than the number of attributes. If the number of attributes is 4, we should take 3 dummies. So number of dummy variables should be equal to the number of attributes minus 1. In this case, as we have done before also, we simply we create one dummy variable. There are two periods, var time and peace time, and the dummy variable will have a value 1 if it is a var time, and the dummy variable will have a period 0. d1 will have a value 0 if it is peace time. Again, we have done one more example. In the case of seasons, there are 4 seasons. So what we should do, we should not have 4 dummies, rather we should have 1, 2 and 3 dummies. So this was all about our discussion on dummy variables. We have seen how Chow test was done and how we can use the knowledge of dummy variables in order to do things in a much more better way, where you want to find whether the change is in the intercept or in the slope or in both of them, or there is no change in any of them. Then we have seen its uses in seasonal analysis, in piecemeal regression, and also we have seen in stability of the function and what is your interaction term. And then finally we had a discussion on dummy variable trap. So with a certain guidelines that if the number of categories you are having is 2, then we should have one less dummy variable, that we should have one dummy variable. Or if you are having a category wherein there are 4, in a situation where there are 4 categories, we should have only 3 dummies. With this, we end our today's lecture. Thank you.